Well, welcome to our first non-review chapter of Precalculus. We have a significant number of learning targets in this introductory lesson. So rather than read through those, I'm going to go ahead and just jump in so we can try to limit this video to be as short as possible. So first off, let's go ahead and review what we should already know about function notation and what a function is. And a function is basically a mapping or a rule that assigns every element in the domain a unique element in the range. And to determine if a graph is a function or not, we use what's called a vertical line test. If we're examining a function or a relation graphically, that vertical line test, if the graph crosses that twice or more in any point, it's not a function. And if it only crosses once, then it is a function. So let's take a look at some examples. A relation is any set of ordered pairs. So we have some examples here of some relations. We are asked to state the domain and the range of the relation and tell whether or not it is a function. So remember, the domain is the set of all x values and the range is the set of all y values. The domain you can think of as the inputs or the independent variable. The range is the output or the dependent variable. And so the domain in this example is -3, 4, and 2, and each one of those goes to a unique place, so it is a function. Over on the right-hand side, we can see that the domain has the element 4, and 4 gets mapped to -2, and 4 also gets mapped to +2, so this one is not a function because that element in the domain gets mapped to two different places, so that cannot be a function. All right, so over here we have letter C, we have a circle. Well, this thing, if we use a vertical line test, okay, that crosses twice. You can see there's always 2 points here and here. So no matter where I move that vertical line, it's going to have two intersections on the vertical line, so that is not a function. Here's the domain and range for that, just in case you wanted to see that. And I had already written this down here. This one is a function because no matter where I pass that vertical line, okay, that crosses only one time, so that one is a function. The domain of many functions has all real numbers, and the way we represent all real numbers is that fancy looking R up there, so that just stands for all real numbers. But we do have some restrictions on our domain, and here are three things that will restrict our domain. First of all, we cannot have any negatives under the radicals. So no negative numbers are allowed inside of a radical. Remember, we're in the real number system. We've been talking about complex numbers, but those are outside of the real number system, okay? So no negatives under the radical. No zeros in denominators. We can't divide by 0. And then this one's probably not as familiar to you, but it's no negatives or no zeros in logarithms. So let's go ahead and take a look at example A for the logarithms. No negatives and no zeros. So this value x right here, it cannot be negative, so it has to be greater than 0, but it can't be equal to 0 either. So it has to be greater than or greater than 0. It can't be equal to, so we're going to represent that with the interval 0 to infinity. Letter B, this one's, we're going to look at the denominator here because we have a fraction. We don't want a 0 down here. So -3 would make that 0. So we need to restrict that in our domain. So we cannot have -3 be a value. So anything less than -3, anything greater than -3 is fine, but not equal to -3. So that's how we would restrict that domain. That's how we would write that interval. So you can kind of see why we reviewed interval notation, and that's all coming into play on these. On letter C, okay, on this one, we can actually factor this denominator, okay, and we want factors of 12 that differ by 1. So factors of 12 that differ by 1 are 4 and 3, okay, so one of them's a 4, and one of them is a 3, and the signs are different. The bigger one is minus, so 4 gets the minus sign, 3 gets the plus sign, and we can set that equal to 0. So we would actually get two values that are not allowed in the domain. +4 and -3 are not allowed in the domain. And then I also have here x is greater than or equal to -2. We don't want any negatives in our radical. So if we put anything bigger than or equal to -2, we will get a negative in the radical there. So we don't want anything that's bigger there. So that's going to restrict our domain as well. So here's what we end up getting. Anything that is um, greater than or equal to 2 but less than 4, and anything greater than 4 on to infinity are okay in our domain. So let's go ahead and look at identifying discontinuities in our graphs. And a discontinuity is basically a hole or a jump or an asymptote. Okay, we talked a little bit about asymptotes before. Asymptotes are just vertical or horizontal lines that graphs approach but never quite get to. So a graph is continuous. It's considered continuous if you can go ahead and draw it without lifting up your pencil. So when you think about this, if you can go ahead and draw the entire graph without lifting your pencil or jumping over anything, then it's continuous. And you can see in all of these, there is some discontinuity. Okay, so let's go ahead and define some of these. There's two different kinds of discontinuity. One of them is called removable and the other is non-removable. And so first of all, this first graph is called a removable discontinuity. There's a hole right here in the graph. And even though we have a value up here, f of a, that is a removable discontinuity that we can plug that hole with a single point. And likewise, the next one where we don't have that point above, we just have the hole in the graph, that is also considered a removable discontinuity. And the definition of a removable discontinuity is any kind of discontinuity that can be made continuous by redefining a single point. So as long as it's only a single point that we're missing, it is a removable discontinuity. This one's called a jump discontinuity, and it is not removable, okay, because it takes more than a single point. There's more than a single point missing in there. And then over on the right, we have what's called infinite discontinuity, and that is a non-removable as well because we have asymptotes in there. Anytime you have an asymptote, either horizontal or vertical, that is called a non-removable discontinuity. So here are some examples. It says determine whether the following graphs are continuous or discontinuous. If they are discontinuous, tell whether it's removable or non-removable. Well, this one is a jump discontinuity, right? So that one is a non-removable discontinuity. This one just has a hole, so that is called a removable discontinuity. This one has an asymptote, so that one is infinite discontinuity, and that is non-removable. This one doesn't have any holes or any asymptotes, so that's completely continuous. There's no discontinuity, so we call it continuous. Increasing and decreasing function. This is our next concept. And sometimes we need to be able to analyze graphs and tell whether or not the function is increasing or decreasing at different intervals. And we do this by looking at the x values on the left or on the graph from left to right. So we're looking on the x values from left to right, and then we're analyzing what the function is doing as we are changing our x values. So as we look at this, if we just consider this 1, 2, 3, and 4, our function when we go from 0 to 1, from left to right, is actually decreasing on that interval from 0 to 1. And 0 is included, 1 is not. You see that there is a discontinuity there. And then we're going to jump up here. Now from 1 to 2, it's not changing at all. So that one is constant from the interval from 1 to 2. And then from 2 to 3, it looks like we're increasing. And then from 3 to 4, we're increasing again. So increasing on the interval from 2 to 3 and 3 to 4. So you're just looking at what's happening with your x values. The next concept that might be new, we talked a little bit about this in the very beginning chapter here in our prerequisite chapter, is called boundedness. And there are three different kinds of boundedness. There's bounded below, bounded above, and bounded. So whenever you're bounded below, that means that there's a y value that is smaller than every other y value on the function. What that means is the graph has a bottom. So here's an example of a bounded below function. That just means there's a lowest point, there is a bottom to it or a floor. If it's bounded above, that means there's a y value larger than every other, so it has a maximum point. And here's an example of that. If we just invert the last one, that has a boundary at the top. So that is bounded above. When we say it's just bounded, that means that it's bounded both above and below. So usually there's some kind of an asymptote above and below that bounds each of those, the graph in each direction. So next up is local and absolute extrema. So at this point, we've already talked about our learning targets 3, 4, and 5, and our next one is the local and absolute extrema. When we say the word local, that means the same as relative. So you'll see sometimes it'll be referred to as relative extrema, sometimes it's called local. That means the exact same thing. And what the extrema are is they are just maximum or minimum values on a graph. Okay, so we're just talking about maximum and minimum values. If it's a relative extrema, that means that the y values are bigger or smaller than the y values that are near it or close by it. An absolute extrema means it's the biggest one or it's the smallest one compared to all the other y values. So let's take a look at an example. Here's example 5. Using the graph below, on this interval from A all the way to B, so I know it goes from A to B and then we have C, D, and E inside here. They want us to label the function as relative or absolute extrema. So the function at A, is that the lowest point, highest point, or just a lower high point? Well, if you look at all the other graph points, this is the absolute lowest on this graph. So that is a absolute minimum. Let's go all the way down to B then. Is that an absolute maximum or a minimum, or is it just relative to the rest? Does it fall somewhere in between? And it's going to a minimum, so it's a relative minimum. At C, we're going to look at point C. It's not a maximum, not the absolute maximum. This one is higher, so this one would be a relative maximum because it's a peak, it's bounded above. At point D, again, this is going to be a minimum. So, and it's relative to the rest, it's not an absolute, so that's a relative minimum. And lastly, at point E, this one's the very highest point on this whole function, so that's an absolute maximum. So hopefully that was pretty straightforward. Next up is symmetry, the concept of symmetry, and that has to do with things that look the same. We have 3 types of symmetry. We have odd symmetry, even symmetry, and those are the most important ones. And then we also have, odd function and even functions. And then we also have symmetry where it's not a function, and we'll talk about that one last. So let's go ahead and we're going to look at all 3 methods to describe our symmetry, both graphical, numerical, and algebraic. And so our first type of symmetry is called even symmetry or even functions, functions that are even. And what that means is there's symmetry with respect to the y-axis. So let's just suppose we have this graph, okay, and we have a point on the graph. I just labeled it AB. If that point exists on the graph, then there also has to exist symmetrically on the other side. This is symmetric about the y-axis. Another point where it's the opposite A value and the same B value. So numerically we would say, if we have this point, let's just say if we put in x equal 3 into our function and we get out 3, so if this is has the coordinate 3, 3, then we know on the other side we must have the coordinate negative 3, 3. So that's all that's saying. Numerically, that's how we would represent that. Algebraically, we would say if we put in a negative x, we get out the same function. So if we put the opposite of x in, and this will make more sense when we get into proving some things later on. Odd functions, let's say we have this graph. If I have this point on the graph, then I must also have a point. This is symmetric about the origin. I probably should highlight this to show you exactly the important point here. This one's symmetric about the origin. The last one was symmetric about the y-axis. So this one, if I have the point AB and it's symmetric about the origin, then the symmetry I'll have is negative A, negative B. It'll be down here in quadrant 3. And numerically, we would say, okay, let's say this point has coordinates 4, 3. If I put in 4 and get out 3, then I must also have the point F of negative 4 gives me negative 3. Okay, so that's just saying if 4, 3 is a point, then negative 4, negative 3 must also be a point on the graph. Algebraically, we would represent that if we put in the opposite of x, we're going to get the opposite of the function f of x. Okay? So again, I don't expect this to make sense until we get through some examples on this. Number 3, graphically, let's say we have this function, okay, and we have a point AB, and this time it's not a function because of a vertical line test, okay, If AB exists, and this one would be symmetric about the x-axis in this case, then we must have A negative B. Okay, so you can see that those are symmetric about the x-axis, which makes it not a function. So algebraically, we're not going to write any function notation. But numerically, if 2 and 3 are on the curve, then 2, negative 3 must also be on the graph. So hopefully you can kind of make some sense of that. To prove a function is odd or even, we have to use algebraic skills. Okay, so we're going to go ahead and go into that next. And example 6 says, prove each function is odd, even, or neither. So what we're going to do on this one, we have f of x equals 5x squared plus 5. So what we want to do is plug in f of negative x, and let me just remind us here, it's even if we put in negative x and we get the same function we started with, f of x. It's odd if we put in negative x and get out the opposite of f of x. So that's kind of where we're headed. So let's go ahead and take a look at this one. The first thing you want to do to prove these are odd or even is go ahead and write, you're going to plug in for x. You're going to plug in negative x. Anywhere in the function there's an x, you're going to write negative x. So I'm going to go ahead and do that in a different color here. So I'll choose red for this one. So I'm going to plug in a negative x anywhere there's an x. Okay. When I do that, what is negative x squared? Well, it's just positive x squared. So I get 5x squared plus 5, right? So I ended up with the exact same thing. So f of negative x, when I put in negative x, I ended up with the same function. If you compare the first function with what I ended up with, this is the exact same thing. So is this odd, even, or neither? Well, it says that if we plug in negative x and get the same f of x out, this is an even function. So we have just proven that that was an even function. All right, let's go ahead and take a look at the next one. G of x equals x squared plus 8x plus 12. So the first thing I want you to do is just rewrite this. Instead of g of x, put in g of negative x, and then rewrite your whole function, but instead of wherever there's an x, put parentheses. Okay, and in those parentheses, what we're going to put is we're going to put that negative x. So we're substituting in the opposite of x anywhere that there's an x. So now when we go ahead and simplify that, negative x squared, that's the same as just x squared, right? When we have a negative x and we square it, we get positive x squared. What about this one? When we multiply this one, we get minus 8x, and then we have plus 12. Now let's take a look at what does this give us. Let's compare that to our original function. And our original function was x squared plus 8x. So it's a little bit different here. So this is definitely not an even symmetry. How about odd? When we plug in negative x, do we get the opposite of f of x? Well, the opposite of that would have all three of these signs as negative, and that's not the case either. So this is a neither. Vertical asymptotes is our next topic. So vertical asymptotes, and we talked about an asymptote is basically a line. And if it's a vertical asymptote, it's a vertical line that a graph approaches but never gets to. So we want to graph this function, it says graph this function. What happens at x equals negative 3 and y? Well, let's go ahead and take a look at that. Let me pull up my graphing calculator here. And let's see if I can pull it over here. And we want to put in that equation. So we want to put in y equals 1 divided by, and make sure you use your parentheses here, divided by x plus 3. And close your parentheses, and then we're going to hit graph. And something's going on at negative 3. So what is going on in this function? If you take a look at that, okay, at x equals negative 3, we're getting something going on there. And what is it that's going on? Well, it looks like we have a vertical asymptote, right? Why is that happening? And the thing you need to be able to state is this. You need to be able to recognize that at x equals negative 3, we get 1 over negative 3 plus 3 if we substitute that in, which is 1 over 0. And so whenever we have a 0 in the denominator like this, that is a vertical asymptote. And that will always be the case. When you have a 0 in the denominator and a non-zero number in the numerator, you will have a vertical asymptote at that value. Okay, so that's your reasoning why. Example 8, let's go ahead and take a look at this one. And example 8, I want to pull that graphing calculator back up, and we're going to change our equation here a little bit. And I want x squared, I need parentheses here. I forgot to hit insert again. X squared minus 9 parenthesis divide parenthesis x plus 3. Okay, and then we're going to go ahead and graph that. Well, what's happening there? That looks a little different than what we had before. So in this case, it looks like we don't have any vertical asymptote. Well, why is that? Shouldn't we have a vertical asymptote at x equals -3? Well, one of the things that we can do is we can actually go in here under our second calculate, our second trace. Let's calculate a value. Okay, so just hit enter, option 1. What happens at -3? I want to know what happens at, and I don't know if I hit the negative right on there or not. Let me see. -3. It might give me an error if I don't use the right negative there. Why didn't it give us a y value? The y value is not displayed, and the reason for that is there's a hole in the graph right there. Okay, we can't really see it on our calculator very well, but there is definitely a hole at x equals -3. That value does not exist in our graph. Okay, so right here at x equals -3, there's somewhere in there on the y value, there's a hole in the graph because it's not representing that here. If you were to look at the table value for this, you would see that it would say error. Well, what is going on in there? So actually, if we look at plugging in the function value at x equals -3, okay, let's go ahead and do that. Let's plug in g of -3 into this function right here. I'm going to replace wherever I have an x, I'm going to replace that with a -3. And I'm going to show you what's going to happen to this. I need an x value down here, +3. So I said we're going to put in wherever there was an x, we're going to go -3, right? Well, what is -3 squared minus 9? Well, this gives me 9 minus 9 over -3 plus 3, which is 0. Well, that looks like it should be a vertical asymptote, but we actually have a 0 in the numerator as well. So this time we have 0 over 0, and every time you have 0 over 0, that represents a hole in the graph, okay? So if you have a non-zero number in the numerator and a 0 in the denominator, that's a vertical asymptote. When it's 0 over 0, then that's a hole in the graph. So let's take a look at what's going on here. So vertical asymptotes, they occur in rational functions whenever we have a non-zero number over 0. But if we get 0 over 0, that's when we get a removable discontinuity called a hole. Okay? So, end behavior, last topic here. Let's talk about end behavior. End behavior talks about what happens at the ends of a graph. So as x gets really, really big or really, really small, what is the function doing? Okay? So this example asks us to describe the end behavior of the following graphs. Well, this graph, as x goes to positive infinity, as x gets bigger and bigger, bigger, the end behavior of that thing, it's getting bigger as well. It's going to infinity. How about on the negative end? As x gets really, 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 really small, it's still going to positive infinity. So this is how we would write that. I hope you're familiar with this notation. It says as x goes to infinity, f of x goes to infinity as well. So as x gets big, the function gets big. As x gets really small, the function gets really small. You have to be able to write it in that notation, so make sure you're familiar with that. The graph in the middle, as x gets really big, it goes to positive infinity again. As x gets really small, this time it goes to negative infinity. Over here on the right, as x gets really big, it goes to positive infinity. As x gets really small, it looks like it goes to x equals -3, or the function equals -3. So that is end behavior. There's another way of writing end behavior, and that is called limit notation. So limit notation is just another compact form or way of writing end behavior for functions, and you will use that in calculus a lot. You'll study limits. So in this example, we want to rewrite the given end behavior using limit notation. So here's the limit notation. It says as the function goes to infinity, or as x goes to infinity, the function goes to negative infinity. So the limit notation, basically what you're going to do is you're going to write lim, and you're going to write f of x. So as the function goes, or excuse me, as x goes to positive infinity, the function goes to negative infinity. And that's what this says. As x goes to infinity, that's right here, the function f of x equals, it goes to negative infinity. So the bottom line we would write the same way. As x goes to negative infinity, so we'll have negative infinity here, then the function goes to positive infinity. Okay? Over on side B, as x goes to positive infinity, the function goes to positive infinity. As x gets really small, the function goes to 0. So those notations would be written in this way. Okay? So that's the format for limit notation, and hopefully you'll be able to go ahead and write some of these end behaviors in limit notation. That'll do it for this video. Thanks for hanging in there. This was a long one. See you next time.